sheet. Don't put it just the last minute. As you study, add things to your cheat sheet, make notes. That's very important. Okay, so I'm gonna solve just one simple example. Maybe I give you some time to think about it right now. Suppose that we have a symmetric signal. So we have g of t, which is symmetrical even. Then prove that g of f is real. Use properties of Fourier transform to show. So if g of t is even, meaning that if you have a signal like this in the time. Okay, so in the time your signal is symmetric, maybe a pulse is symmetric, triangle is symmetric. Then when you get g of gf, it's all real. So you don't have any phase and everything. Like for example, the sinc function. Remember for the pulse, sinc is real. Yeah. That is very real. Of course, if I shift this one, it's going to be a shifted pulse, meaning that if my pulse is here, let's say 2 seconds, then what do I have? If it was symmetric, I had, for this pulse, I had a sinc. But then when I shift it, what happens? When you shift the signal in a time, you multiply by h bar. So you're going to get sinc time e minus j 2 pi f, and then the amount of shift, whatever. For example, this is 2, so is this real? It's no longer real because you have exponential complex. Okay, but if it was symmetric, if it was like around 0, symmetric around 0, you would have just the real. After the shifting, it's no longer symmetric, so you're gonna have a complex. Okay, but why is that? Just very simple properties. Why this is the case? Just think about it when you So first of all, when we say signal is even, what do we mean by that? What's the formula? Yeah, symmetric. What's the formula? G of t is equal to g next. Right. So always when you have to prove something, start with your assumption and see what you can get out of your assumption. Okay, gt is even. It means g of t is equal to g of negative t. And then you want to prove something in the Fourier domain. So somehow I have to relate this to the Fourier transform. So let's take a Fourier transform. What's the Fourier transform of gt? Let's say it is gf, capital Gf, from the properties of the Fourier transform. What's the Fourier transform of g of minus t? Anybody remembers? Which you don't have to remember actually. You can just refer to one of the tables and you see that when you negate the time, what happens? You get g of negative. Right. So this is coming from the table. One of the table properties. Okay, good. So now if these two are equal in the time, gt is equal to g minus t, what do you conclude? Yes. So if the right side are equal, if these two signals are equal, the Fourier transform is also equal. Everybody get it? It's symmetric, so these two are equal. So therefore, this side is also equal. So we can say since, for example, the left side are equal, signal are equal, then the right side, which is computer transform, is also true. So the Fourier transform are equal. So we say GF is equal to GR negative. Okay. But this doesn't mean that we have a real. So yeah, question?
So it's not g of f is equal to the magnitude of negative?
Not yet. Not yet. But anybody can continue after this? To prove something is real, what should I prove? When something is real, GF is equal to its conjugate. So this is what I have to prove. When something is real, it's equal to its conjugate. But this is not done yet. But we know something. For all signals, we have conjugate symmetry. We have conjugate symmetry. Anybody remembers that property? The name suggests, you don't have to remember. Conjugate symmetry. Symmetry means GF and G minus F, but it's a conjugate. So one of them can be conjugate. Doesn't matter which one. I don't remember, it's just the name tells me everything. Conjugate symmetry. Instead of being symmetry, it's conjugate symmetry. So one of them is conjugate. Okay, so we are done. And this is for all GT. Just the symmetric one. This is always, for the symmetric one, we have this extra thing like that. So GF is equal to G negative F. G negative F is equal to G conjugate. So therefore, from this conjugate symmetry, let's say relation 1, what do I calculate? Again, GF is equal to G minus F. G minus F is equal to G conjugate. So GF is equal to its conjugate. Which means that GF is symmetric. Okay, so we just put some properties next to each other, and we proved something important. That if your signal is symmetry, again, it means that you have symmetry around 0, then your GF is all real. Any question here? So now I can easily change this in the exam, for example, and I change this to if my signal is odd. Okay, do it at home for yourself and see what you get. If we change GT is equal to odd, or odd signal, what happens? Yeah. Okay, so do that please. So very simple. I mean similarly. If you got the odd signal, what's the change here? Yeah, there's a negative here and then another negative here and then you just continue. Okay, so you have to prove if it's odd, then GF is odd imaginary. Imaginary means that like it's like J times something. There is no real. Basically, if something is all imaginary, itself conjugate is minus itself. So you have to do this. When something is imaginary, for example, 2J. 2J is totally imaginary, right? So if I conjugate that, what will I get? Minus 2J. So I get negative of that, right? But if I had something real, for example, if I had 2 plus 3J, if I conjugate that, then I get 2 minus 3J, which which is not the negative of that. So this is true only if you have the only imaginary part. Everybody get it? So if you go back to the document that I have for complex numbers, you will see. So a signal is real if z is equal to z conjugate. It's all imaginary if z and z conjugates are negative of each other. So please work on your complex number proficiency. Okay. Study complex numbers. You can look at my note on the 24/6. Okay, good. So if there's no question, I start chapter 4. I'll be in my office on Friday. Please stop by with your questions. I never see anybody, basically. Rarely I say. So maybe that means that I do a really good job in the class, so you don't have to come after hours. Or, I don't know. I hope that's the case. But please come stop by Friday.
What time on Friday? Whenever.
Anytime after 10, 11. Okay, chapter 4.
Is the chapter 4 going to be on the midterm?
No.
Okay.
No, not on it. Okay, so chapter 4 is about amplitude modulation and demodulation, AM. We already talked about it in the previous chapter, but we're going to go into more detail about that. Okay. So, baseband communication. So, what's a baseband communication? Baseband communication is when we have the original signal. So, when I'm talking and I have some original signal, this is in the baseband. So when I look at let's say this is GT, and then I take the Fourier transform, I look at a spectrum, and usually it includes low frequency. So it has low frequency components, and this is called the baseband signal. Baseband. If I later on multiply by cosine, I shift it to some other frequency, then it's gonna be high frequency, and then it's not gonna be baseband anymore. But the original signal is called the baseband signal. So in baseband communication, message signal are directly transmitted without any modification. The original signal, low frequency, usually is transmitted. So most baseband signals contain low frequency content and cannot be sent efficiently. So if I'm dealing with a low frequency signal, there are some problems. The first one is that when my signal is low frequency, we know the frequency and bandwidth are, wavelength. So when you have an electromagnetic wavelength, lambda, help me on that. The speed of light divided by f. Okay. So we have this. So if I'm looking at low frequencies, my wavelength, this is wavelength. Wavelength is large. When wavelength is large, the antenna should be also large. So the antenna size is in a fraction, let's say 1/4 of the wavelength. So if I'm working with a low frequency, large wavelength signal, my antenna should also go large. And look at these numbers: 1 megahertz, 300 meter antenna, 1 gigahertz, 30 centimeter. Yeah, so the higher frequency, the smaller antenna. But so 1 megahertz is a 300 meter antenna, which is not practical. So therefore, I cannot send the 1 megahertz signal in its original baseband. I have to move it to higher frequency so that the antenna becomes smaller and smaller. So this is one problem. Therefore, I have to shift the baseband signal to higher frequency. And the other reason, anybody remembers the other reason for moving the baseband to high frequency?
The interference, right? With other signals?
With other signals, yes, very good. Basically, we want to share. I have a shared spectrum. Okay, we have a shared spectrum, and if everybody just sends in the baseband, so all the signals will collide, right? But if I somehow can assign different frequency or different carrier frequencies to different signals, then they can share the spectrum. Share the link. Okay, so these two reasons, one practicality of the antenna size, and then the other sharing the spectrum, results into go to higher frequencies.
Next question.
Yeah.
When you go to those higher frequencies, do you need to like have a larger capacitor value to be able to react to the frequency harmonics, like what we were seeing in class? Like when we go to a square wave, the edges are lost because the frequency is so high. Is that like the same pacing with like a sine graph? If you go to like a 1 gigahertz signal, do you need to increase the capacitor value so it can react to the signals faster? Or okay, so I'm making the right connection. Okay.
You have to accordingly change your the circuit voltage. Okay, so yeah, so modulating several baseband signals and shifting their spectra to non-overlapping bands allow many users to share one channel to frequency division. This is called a frequency division multiplexing. I guess we introduced it before. Frequency division multiplexing. So basically we multiplex all the signal in the frequency. Okay, great. So this is the motivation that we have to go from the lower frequency baseband signal to something which is much higher frequency. Okay. And this is called the carrier modulation, basically communication that uses modulation to shift the frequency spectrum to higher frequencies called the carrier communication. So you have to have a high frequency carrier to somehow carry your signal from the low frequency to high frequency. So we can have different kind of basically carrier communication, amplitude modulation AM, phase modulation FM, and frequency modulation FM and phase modulation PM. So we're going to study all these three in the next few lectures. And this is just one simple example. This is your low frequency baseband signal. So this is baseband, which is, remember, we said low frequency. Now, when you modulate here, this is also just in the time sky. It's moving. This is AM. So in AM, we modulate with the high frequency, but the amplitude here is corresponding to the amplitude of my baseband. Okay. But FM, as you see, the amplitude is fixed, but the frequency here is lower frequency, higher frequency. The frequency is changing based on this. Okay, we're gonna see it. So if I have a large amplitude here, the frequency is gonna be large. If I have a smaller amplitude, the frequency will be small. Okay, so that's how we somehow modulate or embed our information, our low frequency information into a high frequency signal. So this is FM, this is AM. Okay, make sense? Good. And I'm sure everybody knows AM and FM radios. You have similar symbols. So this is based on. So AM, FM. FM and PM will be studied in chapter 5 under the angle modulation. AM is going to be chapter 4. Yeah. Okay, as you know, everybody probably knows because we have seen this several times. If I want to shift a spectrum from low frequency to high frequency, what should I do? If I have some GM, low frequency, and if I want to move it to high frequencies, from here to higher frequency, what should I do? Multiply by cosine. Okay, so please, everybody should remember this. You're going to see examples in the midterm maybe, and also in your work, your studies. Always when you want to shift from low frequency to higher frequency, you have to multiply by cosine. Okay. So therefore, m of t, my signal, mt is my original signal, the low pass. So mt is the low frequency baseband, my original message. But then it's multiplied by the cosine. So when you multiply something by cosine, you remember you are going to shift the spectrum to the left and right. So you're going to have m of f minus fc and then m of f plus fc. So basically, if this is m of f, you're going to shift it to the right, and you're going to shift it to the left, and then there is a 1/2 here, 1/2 there, fc minus fc. Okay. So this is exactly this one. After modulation, this is your spectrum, which is in the higher frequency. And f of c is called the carrier frequency, the high frequency that carries your signal. Okay, so this simple multiplication allows shift of the spectrum, also changes the amplitude. Changes the amplitude is proportional to the message. Yes. So now this cosine that you have, originally you had a cosine like that. Let's say it was a high frequency cosine, right? Then when you multiply these, we have seen this before. What happens? Anybody remembers?
T forms an envelope.
What's that?
It's an envelope.
Envelope, yes. So the places that I have one, correspondingly, I will have those. And then there's a minus one here, so it's like these are multiplied by that, so it's like an inverted version of that. And then between these points, I have some oscillation. Okay, so my message, this is the very nice thing about AM. My message is actually the envelope, or the peaks of this high frequency signal. You see? So whatever exactly you have here, is what, again, I repeat why is that. Let's say cosine is 1 here, right? So it's going to multiply by this one. And then again, this cosine is 1 multiplied by that one. Cosine is 1 multiplied by that one. So I'm going to have definitely these points. And then here cosine is negative 1. So it's going to be multiplied by this. So it's like inverted here. This one is inverted. So somehow it's like a mirror here. And so these are the points corresponding to cosine being negative. And everything else in between is multiplied by some number between 1 and negative 1. So it's going to be something like that, high frequency. Okay? Everybody got it? So this is the, again, like a nicer picture. But so the things that you have to remember, this m of t is always your envelope. Then also here negative. So this is minus m of t. This is m of t, and then the fn, the high frequency, or a, I'm sorry. The high frequency is oscillating between these envelopes. Okay. So now, in addition to AM, we also have FM and PM as we thought. So in all these cases, basically we are changing something about the cosine. So we have a carrier frequency as the cosine function or sine function, and each cosine has amplitude, it has frequency, it has phase. So now if I change the amplitude, then the modulation is going to be AM. If I change the frequency, it's going to be FM. If I change the phase, it's going to be PM. Okay. So there are 3 parameters. Again, I repeat it, amplitude, frequency, phase. Message can be used to modulate any of these 3 parameters. If my signal appears in the amplitude, meaning that the AT there, that's a modulated signal. If the amplitude includes my message, then it's AM. If the phase of that modulated signal phi t. If the phi t includes my message, okay, so somehow I embed my message in the phase of that. It's gonna be PM. For FM, so we will see in the next chapter that the frequency is basically the derivative of the phase. So therefore, if I want to embed my signal in the frequency, I have to embed it in the derivative of f of t. So df over dt, which is in the nature of frequency, now has my signal. Now you take the integral, so phi t is gonna be the integral of the message. So in other words, the message appears here, in the integral of the message appears in the phi t. So this is the effect. We are gonna see it next time. So this is the basis of modulation using the cosine. Either modulating the amplitude, frequency, or phase. So now back to AM, my message appears on the amplitude and 2 times cosine. So this is like a black diagram. This is my modulating. By the way, my message is called a modulating signal. Again, this cosine omega ct or f2 pi fct. This is the carrier frequency, and then the output is modulated signal. Modulating signal, modulated. So this modulating signal again, MA. Let's say if this is the baseband spectrum. After multiplication, we have 2 replication of that. So now if you look at these, we have upper sideband and lower sideband here, and then the mirror of that, this is corresponding to the lower sideband and upper sideband. We have that. And also, if my original signal, modulating signal, has a bandwidth equal to B, if my original signal has a bandwidth of B, again, what's the definition of a bandwidth? Bandwidth is the maximum frequency that I have some frequency component. So here, if I stop here, the bandwidth is B. If my original signal has bandwidth B, now after modulation, again, remember, you come to FC, and then I repeat this. So now, what is this one? What is this frequency? Anyone can tell me?
FC plus B.
I have shifted everything to FC. So this is FC plus B. This is FC minus B. Okay. And here, the difference between the minimum frequency and maximum frequency is how much? If this is B and this is B, how much do you have? 2B. Okay. So now, therefore, somehow the bandwidth is double. Okay, now let me correct my statement. So the bandwidth is basically like in this case, yes, bandwidth is the maximum frequency, but in this kind of scenario, which we are in like somehow not in a low frequency but in the mid frequency, the bandwidth is the difference between the maximum frequency and minimum frequency that you have values. Okay, so you know your bandwidth is 2. Okay, so the property of AM is that when originally you had the original signal with bandwidth of B, now your modulated signal has a bandwidth of 2. So the bandwidth is double. Is it a good thing or bad thing?
Bad.
Bad, because it means that it's occupying twice the bandwidth on your channel. And again, remember, like the bandwidth is a very precious, I don't know, something. It's very precious. Anyway, because remember, like all these companies, they buy bandwidth. Okay, so now if somehow my signal occupies twice the bandwidth, so it's like they're paying twice for buying that amount. So it's not good. So this is a disadvantage of AM that basically doubles the bandwidth. But of course, we know the advantages. Yes, in talk about that. Okay, so from this slide, you have again upper excited, USB, LSB here and there, and the bandwidth is 2B. Now you see the envelope here, M of T and then minus M of T. Okay, now let's look at the condition on the f of c. Can f of c be, let's say, very, very small? Can I pick an fc like this? And then I shift my spectrum like that. Do you think this is a good kind of modulation? So after this, what I'm gonna get is something probably like that. But the original signal has a spectrum of like that. So originally I had this. In this figure, this is just two replication, the same exact same shape, so I can always recover this. But if somehow there is an interference between this, is this good? Is this similar to that? No. So basically, this is what we call interference. So that signal that my message has been interfered. So this is not a big case. So therefore, what should be the condition on FC? So this is B, this is negative B. So basically, when I shift these to the left and right, they shouldn't collide. So this is if I shift this exactly by amount of B, if my FC is B, I shift this here, then I have this, and then have correspondingly. At this point, I don't have any collision interference. But if my FC was a little bit smaller, then I will have some interference. So therefore, I conclude that f of c must be greater than or equal to the bandwidth. Okay, so So this is the original spectrum. After the AM modulation, it's going to be shifted to the right and left, right? So if my f of c, the carrier frequency, is large enough, so B and X. If my f of c is really, really large, so I'm not worried about any collision, right? Because these 2 points are far away from each other. However, as I make the f of c smaller, so this comes to the left, this comes to the right, and the probability of collision becomes larger and larger. So this is the limit, that they just meet each other. And what's the value here? The value here is exactly, this is B, this is B, B, B. So f of c. So at f of c equal to B, we are exactly at the point of meeting. But if I make it f of c smaller, then they're going to be collision. So therefore, f of c must be at least B. Who got it? Nobody? Really?
Yeah.
Yeah. Yeah, so the main point again is that when you shift them, they should be separate. They shouldn't collide. If they're separate, we are fine. So f of c greater than b to avoid overlap of the modulated spectrum. If f of c is less than b, then two copies of the spectrum overlap and information of MT is distorted. So again, so if f of c is less than b, like here, then these two replications, they overlap at this point. You see, they overlap and my data is distorted. Because I never can get, when these two are added up together, I no longer know what is what. Okay, where is my original signal? It's lost. Okay, so if carrier frequency is smaller than band B, then two copies of the spectrum overlap, information of MT is distorted, which makes it impossible to recover M. Okay, now the demodulation. The demodulation is very simple. So this is after modulation, so I have two replicas at Fc and minus Fc. So at the demodulation, I want to get my original signal back, my baseband signal back. So somehow I have to shift this to origin. And we know the shift of the spectra is done by cosine. So I could multiply my modulated signal by another cosine. So after multiplying this by another cosine, what happens? This is, the whole thing will be shifted to the right, and the whole thing will be shifted to the left. So if this is shifted to the right, the amount of Fc, this goes to 2Fc, and this one goes to origin. This is that when we shift it to the right. Now if you shift the whole thing to the left, this one goes to minus 2Fc, and this one goes to the origin. So you have two of these exactly the same thing in the origin. That's why you get A, and then you get half of that here and half of that there. So this is A over, A over 2, and this is A over 2. Why A over 2? If this is A, why do I have A over 2?
When it originally split, it dropped the amplitude in half.
Mm-hmm. Yeah, basically when we multiply from the Fourier transform of a cosine, when you multiply a signal by cosine, then the spectrum is divided by half. Half here, half there. Half to the right, half to the left. And like that. So when I originally had this one, and I multiply by cosine, so I got A over 2 here, A over 2 there. So this is A over 2, this is A over 2. So why is it A?
Constructive interference. They like combine and like.
Yeah, so there are actually 2 of them exactly, very good. So one A over 2, and then exactly the same thing on top of that A over 2, because 2 of them come here. That's why you get A. If I'm going too fast, please let me know. But because we have seen this before, everybody got it? To the right? Okay, look at it. So I had, let's look at a triangle. Fc minus Fc. This is my original. This was MF. Okay. After modulation, I had, so after once in the time domain, I multiply MT by some cosine. What happens in the frequency, I have half of it here, half of it there, shifted to Fc and minus Fc. Now if I multiply this by another cosine, so MT now cosine is squared, frequency, because I'm multiplying by cosine, again shift to the right, shift to the left. Shifting the whole thing to the right. The whole thing goes to the right. This one will be mapped to
2FC.
FC. So FC added with another FC to FC. Minus FC added by FC goes to, so shift the whole thing by amount of FC. So then this one will go to this one will go to 2FC. But then because of we have a half, so this becomes A over 4 and this becomes A over. Okay. Am I done? No, because I only shifted to the right. Now you have to shift the whole thing to the left. Again by FC to the left. When I shift this to the left, this one goes to minus 2FC. Again, A over 4, because it's going to be half. And then this one goes to shift by FC to the left.
0.
Origin. Exactly the same. So therefore, at the origin, I have two of them. Exactly the same thing added together. So you get what? You get twice of that. So this is correspond to having these larger because multiplied by 2. A over 2. And of course, you have A over 4 here. Okay? Done? Everybody got it? Okay, so therefore this is active modulation. So now this is the good thing because I got my original signal back to the low frequency. The modulated one was high frequency. After I cosine by another cosine, I got it in the baseline. So what should I do now? So this is at the receiver. So this was transmitter, high frequency transmitter at the receiver. Let's say your cell phone. Okay, you multiply by cosine, so basically you modulated it, and then so you get a baseline at twice frequency, and your original signal is here. What should you do? You have to get rid of the high frequency. So just put a low pass filter. So you put a low pass filter here to get rid of these high frequencies, and you get therefore your original signal back at the receiver. So again, the big picture here is like that. So here there is a transmitter, or let's say this is you, which you have a message MT. You have a message, and this is, let's say, the channel, the communication. We call it communication channel. So over the communication channel, you should have a high frequency. But then at the receiver, you want your M of T back. So this is MT times cosine. So therefore here you multiply by another cosine, you put a low pass filter to get your M of T back. So now it makes sense. So anybody that listens to me, it makes sense. Okay, so mathematically, so this is S, which was called modulated signal, which MT times cosine. Now I multiply by another cosine, so that cosine is squared, and this is exactly the shift that ones. So shift by 2FC to the right, by 2FC to the left, and then the original. Okay. signal, the other ones are high frequency. I have to get rid of them by a low pass frequency. So this method of recovery is called synchronous demodulation or synchronous detection. Can anybody tell me why there's it means that the like between the transmitter and receiver, as I mentioned, there was the channel, etc. So these two must be synchronous. Okay, meaning that they have to have the same plot and so why is that? Any idea? So let's see what happened again. So at the transmitter, I multiply my signal by cosine of 2 pi FCT. This was the communication channel. And at the receiver, I multiply again by another cosine. No pass filter. I got my signal. So now why do we say that the transmitter and receiver must be synchronous? Transmitter, receiver.
Is it just the same time parameter or whatever? Like same signal with respect to time?
Yes, basically because both of them have to be exactly cosine of 2 pi omega c. If there is a shift here, let's say if they have a phase shift, if there is some theta here, then we don't get exactly this nice property. So our scheme was all working based on the fact that if here I multiply by cosine, I again reverse it by multiplying with the exact cosine. There's no time shift. Okay, so that this is something we call being synchronous, meaning that if for the transmitter the 0 is here and this is a cosine, for the receiver exactly they should have the same time reference and exactly the same cosine. If there is a little bit of phase shift, then this method doesn't work. Okay, so this method of recovery is called synchronous detection, where we use a carrier of exactly the same frequency and exactly the same phase. And the one that was used for the modulation. Okay, now let's see one example. So I have a baseband signal given by mt as cosine of 2 pi fmt. So my original signal is also a cosine. It could be, right? It could be anything. It's a low frequency cosine. Now it says find the double sideband. So DSP stands for double sideband. So this method of double sideband for explanation. Because we have upper sideband and lower sideband, looks like that, so it's called double sideband. Now it says find the double sideband signal and sketch its spectrum. Okay. So this is the original baseband signal. You multiply by. Okay, so before that, what's the Fourier transform of a cosine? 2 deltas. Okay. So MA is 2 deltas. So if the frequency is FM 1 delta, FM 1 delta is minus FM and half and half. Again, I expect you to know this. I mean, in the table you have it. What's the Fourier transform of a cosine? 2 delta. This is the original baseband signal. Now, if I multiply by some higher frequency carrier, what happens? So if I multiply my m of t by cosine of 2 pi fct, This is how the AM works, right? So I multiply by high frequency cosine. So what changes happen in the frequency domain? The spectrum shift to the FC and minus FC. So therefore, if it's FC, I'm going to have 2 deltas at FC and 2 deltas at minus FC. And this is quarter, because during this operation, the amplitude halves. Quarter. Okay. So therefore, I mean, for up until now, we were looking at like a spectrums like that, but it really doesn't matter. Even the spectrum could look like this. Like that. So what is this 1 quarter? Is it the what is this 1 quarter?
The area.
The area. Okay, thank you. It's not the amplitude because amplitude is going to infinity. So it's just the area. So it's somehow the energy. If you take the integral, the energy is just half, but it still is going to infinity. Okay. Yes.
Did you say that was high frequency?
This one is low frequency. But then this is multiplied by a high frequency cosine. Yeah. So this is the carrier, which corresponds to this FC. So this is high frequency. My original cosine has a very low frequency. This is the low frequency. It corresponds to this low frequency, high frequency. So after multiplication, what I have in the time, I have the low frequency one and the envelope, and then I have the high frequency. So it looks like this. Yeah, so this is a nicer picture. So the envelope is the low frequency cosine, and then after modulation we have this. And this is the double sideband modulated spectrum. So what's the condition for not having any interference? F of C should be greater than F of N. Remember, like we said, F of C should be greater than the bandwidth. And the bandwidth here, you have two deltas, Fm and minus Fm, so the bandwidth is F. Okay, so the F of C here should be greater than this. Because if it was smaller, then these two delta would somehow collide. Okay, and then at the demodulation, this is the original signal M of t, which now has multiplied by 2 cosines. One cosine at the modulation and one cosine at demodulation. Multiplies by cosine squared. So the whole thing shift to the left, shift to the right. Remember? Now we have this figure. 2fc minus 2fc and the origin. And this is my low frequency signal. So I could use a low pass filter to get my origin signal back. So if the gain of your filter is 2, and if it's the low pass frequency, so it removes the higher frequency and then compensates for this half, so you get exactly your original signal back at the receiver. Okay, so we possibly have have any question? No? So I continue? Oh. So I guess up to this point, somehow we have used all the properties that we had seen before: multiplication, cosine, exponential, etc. Now here, we introduce some practical ways of doing this modulation. So yes, one case as we saw is that I have m of t, and let's say I have a circuit which is a multiplier. And so I apply cosine to find city. There's a very nice multiply module you buy it, and then it does the multiplication. But in case that you don't have that ideal multiplier, so the question is that what can we do? How can we just get this empty cosine? So there are several schemes. One scheme is just looking at this example. Let's say instead of the multiplier, I have a nonlinear system which is represented by this input output relationship. The output y is ax plus bx squared. Now let's see how this can somehow generate this multiplication for us. So I have m of t, and I have the carrier frequency. I have the adder here. It's not multiplier, I have adder. So mt plus cosine comes here, and then mt minus cosine comes here. Then I have that system which is nonlinear. The output is y1, y2. It's added, and it's going to bandpass. We're going to write the equations. But interestingly, at the end, we're going to get empty cosine. So I got the multiplication that I wanted through some addition modules and some systems. Okay. I guess the reason is that maybe the multiplication is not a very simple or cheap operation. So this is a better option in practice. But let's look at the order. So x1 was empty plus cosine. x2 is empty minus cosine. And then y1, the input is x1. So it's ax1 plus bx1 squared. ax1 plus bx1 squared. This is the output. Similarly, the output at y2 is ax2 plus bx2 squared. x2 and then x2 squared. So if you just square these and do some very simple math, and eventually do the subtraction here, it is y1 minus y2. Please do this at home, maybe it takes 1 minute. But you're gonna see that the result is 2a empty, and then something which is empty times cosine. And remember, I'm interested in this. So what should I do? I somehow should get rid of this part. But the good thing is that they are separated in the frequency. Why? Because this is low frequency, and this is after multiplication, somehow is high frequency. Can I separate them? How can we separate low frequency signal and high frequency signal? Using filter, right? So if I have something low frequency and then I have something high frequency, how can I separate? I'm interested in this one. So just put something which we call band pass filter. Okay, so if I put a band pass filter, which is tuned at the center frequency of Fc, then I can get it out this way. Okay. Great. So that's why you say band pass frequency at the center frequency of minus Fcn plus Fc. So someone you get rid of this. Get rid of this and you get the multiplication. So again, so the goal was to do this m times cosine without use of the multiplier. So this is a nice scheme somebody has come up with to just use the simple operators on systems to just get this. use a bandpass filter Q at FC. The first term is suppressed and the desired modulated signal is generated. Okay, and this circuit is called signal balance modulator, and only one of the inputs does not appear. It acts as a balance bridge. Okay, so they have a name for that signal balance modulator, and it says that one of the inputs. Okay, so we have two inputs, and one of the input doesn't appear. Yeah, cosine doesn't appear, so you have MT, and you have the multiplication. Okay, great. Okay, but the point is just how to work with this system and just the idea that okay, this is the cosine that times n that I like it, so I just put a bandpass filter to get just this part. Okay, I guess I stop here. Next time we are going to see another method for testing this modulation. So again, please stop by on Friday if you have any question, or send an email. That's also very convenient for me and you. Send an email, but study really, really hard.